Hey folks, for this screencast, we're gonna do something I've been wanting to do for a while, which is speed up this code a little bit. I think there's a couple things in here that I could do to make the code a little bit faster, and so we're gonna kind of go over that and see if we can make that faster. So basically, the way to make the code faster is to skip all of this in here and basically come down to this loop and basically find a way to make this loop faster. So one really easy thing right here, obviously, is to change the time step. I don't really want to change the time step. Here's where I save the current. Here's where I change this. And by the way, what I'm going to do as well is I'm going to make t final. I'm going to make t final 10 seconds. And I'm going to run this real quick. And it should say tick and talk when it's done. Is it plotting? There you go. Elapsed time is 9.9 seconds. Whoa! All my plots came out of nowhere. Let's break the code before we plot, so we can kind of see what's going on. So where there's simulation complete, I'm just going to do a talk, and a break. I think that works. I'm going to do main. Break may only be used in a while loop. Okay, let's try a return. Main, that works. Okay, so it's going to do, okay, so there we go. So simulation is 0.43 seconds. Now that doesn't seem like a lot, but if you do 0.43 times 5400, which is an entire orbit over 10, right, now you're talking about 232 seconds. So if we can get that 0.43 number down, and let's go ahead and just simulate 10 times that length so we get a little bit higher of a resolution. So I'm going to do 100 and type in main. And now, there we go. So, okay, 1.5 seconds, no big deal. Now, why is it saying time 1 out of 100? Why am I not seeing more prints? So there's last print, and there's next. Let's see, and next is defined there, which is 100. So I'm going to do 1. And now type in main, and now, okay, there we go. Now I can actually see it go. Notice that when I print, it actually takes a little bit longer. So it was 1.5 seconds when I didn't print that, and when I did, it's 1.6. So that's another way to speed up code, by the way, is to just not print as often. So if we do next is 10, right, and then run main, you know, now it's going to run there, and then still 1.6 seconds. The other thing I want to do is I want to move this next parameter up to the time step, just so I can actually see what's going on. And so now let's get into the weeds here. So I've been messing around for 3 minutes. So this stayed out, not really much we can do there. That we're saving code, we're saving data here, we're saving data, we're saving data, we're saving data, we're saving data. We're saving a bunch of data. This is all for plotting. There's not really much we can do there. This we can change the print statement, and then here the satellite code is really where I think we can shine. So in the satellite code, we extract the state. Not much we can do there. Right here we run quat to Euler, and if we open up quat to Euler, we can probably do, if s equals 4 and s of 2, you do a transpose in there. So this if statement, if we can get rid of it, so error checking is one thing where, you know, you really run into a lot of issues. So there you go. So rather than doing the error checking, let's just send the code, the transpose, and that should just do it right away. And now that's 1.65. I think it was 1.68 before. So we saved a little bit of time with that if statement, pulling that out. Now we can run into a lot of issues. This real statement here, are we running into trouble there if we run that? No, so we can get rid of this real thing. Again, bad things can happen if we're not simulating properly, but that saved us 0.2 seconds right there. So that's pretty awesome. And again, so let's look at this. So we were at 1.68 for 100. If we do 5400 over 100, we're talking about 90 seconds. And then now that we're at 1.46, you know, we've just shaved off, for a full orbit, we've shaved off 12 seconds. So we're doing pretty good here so far in terms of speeding up the code. All right, so then we're still extracting states. We're extracting states. We're building a matrix. We're multiplying. This right here. Why are we running planet over and over and over again? These variables should be global. So what are we using? Can we, how do you like view left, right? Fantastic. So I'm going to put planet, wait, what the what? What the what? Left, right? Okay. Over here, I want to see planet. Do I have to like drag? Oh my goodness. I have no idea what the heck I just did. Okay. X out. If I open, what do I want to open on the side? Planet? No, what the what? Now we're talking. I see what's happening. Okay, over here. Okay, I was supposed to hit, this was like a view, you could see the same code at the same time. Okay, so now we have satellite over here, and I still want none. Okay, and why do I need planet? I think it's because I need mu here. So if I just make mu a global, right, and just throw mu in there, and then grab main, and grab mu in the global. There we go, that works. And, ooh, what the heck? Why did that take longer than last time? Okay, it looks like we have some, that's interesting. So my computer is not exactly constant here. Okay. All right, well that stinks. I thought I was saving time here. Now, actually, I have a question. If I get rid of that global, is it possible that it's like holding more information in memory or something? Nah, no, it's just variable. Okay, so that's not right. All right, so let's throw mu in there, and then go over here and throw mu in here. Oh, but then in the satellite code, I need to comment out planet. I don't want to run it every time. There we go. Okay, so we're not exactly making a lot of savings yet. But we are cleaning up the code in a way. All right, so here's the last mag update. So this happens. That again, I don't want to change that because that's just how that works. There's a TIB here. Let's check out this TIB matrix. Okay, so I do have this in place. So cosine functions take a lot of time, so it's good to have those in there. Okay, so that's cool. TIB quad. What's going on in here? Oh boy. Is there any way we can clean that up? Doesn't look like it. I mean, we might be able to do like this, maybe the squareds. So let's do like Q0 squared is Q0 squared, and then like Q1 squared is Q1 squared, and then like Q2 squared is Q2 squared, and then Q3 squared is Q3 squared. And then everywhere we see a squared will change to an S. And then hopefully maybe that'll speed it up a little bit because we only have to do that computation once every time instead of like 5 times. And then that should add up over time. Hopefully we'll see like a significant difference in. This is cool. I just realized Matrix originally adopted from Boom 2010, Mark Costello. Yes, Mark Costello is my advisor at Georgia Tech. He's the chair of aerospace engineering now. So that's cool that he's still like in this code. He lives on. It's awesome. Anyways, so then these multiplied by each other, like Q1 times Q2. I mean, like I guess I could. I mean, is this repeated more than once? There's a Q1 and Q2 there, and then that's it. That seems a little bit over excessive. All right, let's try to run main and see if we didn't break the code. Yeah, we're still hanging around. That was really fast, 1.4. But yeah, we're still hanging around the same kind of time period. Let's see. Then here, last sensor update. Okay, so let's run this sensor block. Okay, so here's a sensor param. So this isn't cool because that means this is running over and oh boy, this is running over and over and over again. Oh, wait a second. So there is a problem, and the problem is that this bias is random every time? Hang on. So you do mag field bias plus mag field noise. So the noise, so the scale factor of the noise is the same every time. And then but the mag field noise variable, oh, weird. So you kind of have to redo this because you take this value times this random, and so you have to do that random in there. Interesting. And that adds that in there. You add the bias and the noise. The bias changes every time? The bias should be a constant. The bias shouldn't be random every single time. So that's interesting. So really we should make a new function. I'm going to do new and call this sensor noise.m. File not found. That's right. I want to make a new one. Oh, did I not hit new? Oops. Okay, so I want to do sensor noise parameters. All right, and so that's going to be this guy. Boom, and then sensor noise. That needs to run every time, and then this guy noise. And then something weird. So the bias is fine. So this is weird. So this should be bias is Euler bias. Yeah, wait a second. Do I have an Euler bias? Oh, weird. Oh. Is it possible that what I wanted to do was like take the bias times that random number and that gives me the noise? Huh. That seems more realistic. I kind of like that. So really what we need to do is go over to sensor noise. Okay, now I'm losing my mind here. Let's go back to what we had before. Okay. So we've got the mag scale bias, and then we've got a different, no, see, we have a different value for the noise. So how I had it before is fine. So we can get rid of this one because it's a different value for the noise and a different value for the noise. And then what's happening here is that this bias is right, but we also need a Euler noise. And it looks like this is like a bias of 2 degrees. And then what, we have a noise of like 1 degree. That look, how does the noise, so the bias is, that's 4e minus 7, so that's pretty low. Which one's bigger? I'm just going to say 1 degree of noise. 1 times pi over 180 times f. So that f there, though, why do I have that in there? I'm just going to put f up here as well. Well, see, this is the thing. Like, I kind of want to make f a global, f sensor. I need that variable needs to be more specific. So this needs to be f sensor, and f sensor, and f sensor, and f sensor. Okay, and then same thing here, f sensor, and sensor, and sensor, and then we're going to do Euler noise. So wait, we have mag scale noise, mag field noise. So I think we need like Euler scale noise, and then we're just going to have, and in the sensor file, you have Euler bias and Euler noise. So you can just do, yeah, that's fine. Euler noise is Euler scale noise times 2 times rand minus 1. Okay, and then what we need to do is sensor params needs to run once, which I think that runs in here. Sensor params, that runs in there. And then we also need to add those as global variables though. So do we have any bias values in here? No, we don't. So we need global, F sensor, mag field bias, angle field bias, Euler bias, and then we're going to do a global again, and we're going to do those other ones. So we're going to grab, let's see, sensor noise, throw that, sensor noise. So I'm going to grab, can I put, where's main? Is main over here? How does this work? Well, main's right here, and then sensor params. Let's see, view, left, right. Yeah, why did it only grab like 3 of them? I mean, yeah, shouldn't I just be able to grab, like there's sensor noise. Shouldn't I just be able to like move this? Yeah, oh dear. Okay, there we go. Okay, that worked. All right, so then we're gonna grab, no, dang it, I grabbed the wrong one. Whoa. Sensor params, I'm losing my mind here. Sensor noise, so there's sensor noise. Okay, we got it. And then main, okay, we got it. So then we're gonna grab mag field noise and ang field noise and Euler noise, right? And then we're gonna copy these 2 lines of code and we're gonna run over to satellite and paste them in there. And then in the sensor routine, we're gonna throw those in there. And we don't need to run sensor params, we need to run sensor noise, which creates the actual noise value. And will that work? Yes, that worked. Not necessarily sure if it went faster, but it is what it is. Okay, so now we got the navigation block. So how does the navigation block work? So you've got s equals 0.3. If the sum is equal to 0, you just take the previous value. So doing a sum is a lot of work. And then here are the bias estimates. That's right, because I don't have like a Kalman filter or anything that estimates that bias. And then this is just a complementary filter. Why am I doing this? Is it because the first time? It's probably because the first time. Nothing. I need a better way than doing this sum. That's taking up a lot of resources. What if we just set like b field nav prev? Like where do we initialize that variable? B field nav prev is 0, 0, 0. What if let's just throw a -99 in there, and then in the navigation block, just say if b field nav 1, 1, and then equals -99, then you do all that, and then after that b field nav prev will be set by this all down here, and then everything should be good to go. I like that. Okay, let's see if the code still works. Okay, we're cooking. Let's go back to satellite. So that's the navigation block. Now we got the control block. Let's open up the control block. Yeah, okay, so here's another problem here, right? We have magnetorquer params that runs every time. And that seems fine, because those are just like little like 3 variables or whatever, but they should, I think I'm okay with that. So that's fine. Reaction wheel params, what's going on in here? Oh boy, that's a lot of computation. That cannot be, there's no way that's necessary. Okay, so why do we need reaction wheel params? PQR nav, let's see, IRR, that's this guy. So that needs to be a global. So where's, so if I do IRR global, if I have a question. If I uncomment this, right? Assume for the moment that N1 is along the x-axis. That's not true anymore. Okay, so if I do IRR and I run this, it should throw an error, right? Yeah, okay, good. So if I just make, because now does the main routine call reaction wheel? Where do we run? There is inertia here. Inertia runs the, okay, yeah. See, so the inertia block runs the reaction wheel params. So if we just go through here and figure out which variables we need in this control block for reaction wheel params, we should be good to go. Okay, so we need IRR, so there's that global there. And then PTP command, PQR command, KD is I45, M desired is KD, PQR minus PQR nav. That should be all fine. And then we've got J inverse. So we just need IRR and J inverse. And then we should be good. So if we go back to main, let me throw a breakpoint in there. So J inverse is an empty. Yeah, see, that's no good. Okay, so we did something wrong. So that means more than likely in the main routine over here, we need an IRR and what was the other one? J inverse. And that should be good. 1.2. Sweet. That's saved. Is that, I mean, can we recreate that? Oh, heck yeah. Okay, that was a ton of savings. Yeah, what was reaction wheel params doing? It was doing a lot, I'll tell you that. Yeah, oh man, it was doing like, oh, it was doing a J transpose inverse? Woof. Woof. Okay, that's wild. Anyway, where were we? We were in the control block somewhere. Control block. So J inverse has worked, right? Because we put the global in there. Let's run main with the breakpoint. Let's make sure J inverse is now a thing. Okay, cool. All right, so we fixed that. That's neat. So let's go back to satellite. Satellite. Boom. And let's look at the whole code. Okay, so yeah, see now we got magnet torque params like thrown in there twice. And it's just because you need max current. So maybe make max current a global variable, so you don't have to do that again. So do max current, and then if we run main, let's see, we're in satellite, right here. Yeah, we need to make all of these very global. I mean, you know what? I'm gonna leave it only because it's not doing a lot of like the max. Those parameters are not doing a lot of computation. I think I'm okay with it. We've created a lot of savings already just with the little things that we've done. Cross, we have to do that. All of these if statements we have to do. That's a lot of checking. No way around this guy with the different variables. Translational dynamics, nothing around there. Yeah, I can't get around that. And then inverse I, we've already computed once. And then that's it. Okay, so if we did this right, so we were at 1.68 times 5400 over 100, so that's 90 seconds. If we can consistently get it down to 1.2, we've shaved off like 35 seconds. So then if I go back to main and I change the period to 1 full orbit, let's see tick and talk real quick. I'm going to pause it for y'all. All right, folks, yeah, so it took 62 seconds. So my math was a little wrong. It's not 5400, it was 5700. So 69 seconds, 62 seconds, I think we did pretty good. So that's awesome. So we've cleaned up the code. So stay tuned for the next video where I finally put in disturbance torques and forces.